welcome back. Today I'd like to take a look at how our measurement of pressure can help us to predict various aspects of the weather, including complex wind structures, and we'll be looking at the relationship between high and low pressure regions and their associated wind velocities and what causes these things to happen the way that they do. And so first of all, when we look at a pressure map, we are often at a different elevation. And so if, say, you're up at the top of Mount Whitney, your pressure is going to be lower here on the average than it'll be at sea level. And then if you go up to Denver, Colorado, it'll be different than it would be, say, at the top of Mount Whitney, but it would be different from what your pressure is at sea level. And so your pressure maps wouldn't make a whole lot of sense if we measured things in terms of the absolute pressure at a particular location. And so what we're interested in instead is the variation in pressure from the norm. So how do we do this? Well, one way you could do it, say if you're at the top of Mount Whitney, is you could dig a hole down to sea level, and then you could drop a pressure gauge down there, and you could measure what the pressure would be 14,000 feet beneath the surface, and so that would correct for the pressure. But what we can do instead is we just look for the average pressure values as a function of altitude. And so we correct for that so that your normal pressure would be the pressure at sea level. So this P atmospheric, which is normal at sea level, would be 1,013 millibars. And we saw before that it's also 14.7 pounds per square inch. Now, if you went to the top of Mount Everest, your average pressure would only be 1/3 of this value. And so what you would do is you would add back in that pressure differential so that you have essentially your pressure is then normalized to whatever your pressure would have been at that elevation. And so, in other words, if the pressure here is normally 813 millibars, if that's your normal pressure, what we would do is we would add 200 millibars to that, so that the pressure that's normal for this elevation could be then compared to the pressure that's normal at that elevation. And so when we see different lines of pressure on a pressure map, what this shows us is the variations in pressure from what's normal. And so that means that we had to normalize this pressure by adding an amount that corrects for the elevation. And so typically, if you had a high pressure region, this might be a little more than 1,013. This might be 1,053 at that highest level of pressure. And then at this next higher level of pressure, this might be 1,033. And then we get a little farther away, we might be down to the normal 1013. But then eventually, if we move in the direction of a low pressure area, then we might go here to 1003. And here we might have 993. And then we would eventually end up in this low pressure region. Now typically, if we're near the surface, the regions of high pressure tend to have wind velocities that move toward the direction of low pressure. And so that is the kind of thing that we're going to be looking at today, is what are the mechanisms by which we get a transfer of air between a high pressure region and a low pressure region. So in order to understand that a little bit better, I first would like to take a look at what happens in a column of air that is associated with a high pressure region. So if this is high pressure, then basically what we tend to have is an inflow of air. Okay, and this might be, for example, the tropopause of air, associated with the boundary between the stratosphere and the troposphere. And so this is associated then with air that is moving down. And so this air, which is coming in, moves down, and it starts to compress and heat the air that is below it. And then here you would be standing below, and if you had some kind of a barometer that could measure the pressure, because the air is being squeezed down on top of you due to this air that is flowing in the down direction, what you would experience is high pressure. And so you would be measuring on your barometer, instead of 1013, maybe 1053. And so this tends to be warmer air that's flowing down. This air is stable because it's being compressed and it reaches an equilibrium. And so the fact that it's stable is an indication of the fact that you don't expect clouds to form. Okay, and so if you have a high then, usually that is associated with clear air. And if it's a warm high, which is the case at lower latitudes, then this might be also warm air that you're feeling with very few clouds and just a pretty nice sunny day. And so that is the basic genesis then of a high pressure region that is associated with air that is moving down. So we can say that in this region of the United States right now, the air is sinking. Now if we're in a low pressure region, like for example, if you're out in Death Valley, the sand is going to tend to superheat, and so that's going to cause the air to become less dense, and so the air rises. As the air rises, it's going to tend to cool. We'll get water molecules condensing. And so you get cloud formation. Now, whether or not this low pressure region means that we have a storm, is something that we probably can't tell from just looking at a pressure map like this. But we can tell that the air is moving up and that it at least is forming unstable stratoform clouds and possibly cumulonimbus clouds. If there's enough moisture content in the clouds, you could, in the associated with this low, you could get severe rain. And so the air rises, then that creates essentially a vacuum down here. And so down here, because the air has left, this would be measured as low pressure. The air rises and then it comes out near the top. And so at the top here, the maximum height that we would expect that it could go would be the tropopause. And it could expand out. Okay, and so we'll tend to see unstable air that is rising in the vicinity of a low pressure region. And oftentimes at the surface, you can have very hot conditions. For example, a lot of times you'll see a low just parked outside of Death Valley, in the vicinity of Death Valley. And so that air is being superheated, causing it to become less dense, to rise up. But as it rises, the air tends to expand and cool. And so that's what causes the unstable clouds to form. So we have stratocumulus or cumulonimbus. And now what happens if these low and high pressure regions tend to be adjacent to each other? Well, in that case, we can have a transfer of air that forms a convection loop. Okay, and so if these things are interacting, they're close enough to interact with each other, then what's going to happen here is that the air near the ground is going to tend to move from high to low. Okay. And so then what's going to happen here then essentially is that that's going to replace the air that rose up here. But because the air is rising here, this tends to cause the pressure to increase. Whereas here, before the air has been compressed, that tends to decrease. And so at altitude, the air is going to tend to move from high to low if these are close enough so that they can circulate around. This goes from low, and then we have this air rising till it hits the tropopause, gets a little bit squeezed there, and generates higher pressure. And then that air is going to come back around and be attracted toward this low, which then becomes more and more compressed and comes back down. And so we get a convection loop. So in this convection loop, we essentially have a complete circuit of the wind. And so essentially what this is doing here is here we're taking heat, we're delivering it to the upper altitude, and then this higher pressure region is going to experience a decrease in pressure in this direction, and that's going to pull the air from high to low. And then here, the high is attracted toward the low because it hasn't yet had a chance, the air hasn't yet had a chance to compress here, but then it gets squeezed down until it becomes high pressure in this area. And so this tends to transfer heat from one location to another. Now, these convection loops can happen on the large scale. In other words, they can happen over thousands of miles and can cover a significant portion of the Earth's surface, as is the case where you have a low pressure along the equator. That air rises up, and then eventually it drops back down again at about 30 degrees north latitude, and you have a high pressure region where that air drops back down. Or it can happen over a shorter distance scale. And so that's what I'd like to look at first, is what happens here if we have one of these convection loops over a shorter distance. The example I want to look at are onshore and offshore breezes in the San Luis Obispo area. Here we have the Pacific Ocean. And then here, right along the coast, we have Morro Bay. And then you go up over the coast ranges to Atascadero, or Paso Robles. And so the light that's coming in from the sun is going to be striking somewhat uniformly on the land and on the ocean. But what tends to happen here is the land has a lower specific heat. And as we learned before, a lower specific heat means that the same amount of heat being input causes a larger temperature change. Because lower specific heat means it's easier to change the temperature of the land than it is the water. Okay, and so this is going to superheat the surface here. The surface gets very hot, the air expands, and it rises. And this leaves behind a low pressure region at the base. And then that air, as it moves up toward the tropopause, gets a little bit compressed and becomes higher at elevation. While that's happening, that low is going to tend to take cooler air from Morro Bay and deliver it up to Atascadero to fill that void. So here's where the void was created that causes the low pressure from the air rising. Here comes what we call the onshore flow. Oftentimes in our area, an onshore flow is going to have a lot of fog in it. And so that will pull fog up over the Morro Bay area and engulf this entire part of the coastline in fog. That's a very common kind of a pattern. And so this is being caused by what we call an onshore flow, which originated because of a disproportionately higher temperature change that the land is experiencing, whereas the ocean here is experiencing much less temperature change because it's near the water. Water has a higher specific heat capacity, and so therefore does not change its temperature as much. And so this air at altitude starts to cool, but the air that's flowing down here is flowing from low to high. Okay? And so we're compressing because we're getting this downflowing air in this area. And so that's coming in to replace the air that was here, but now has come up to replace this air. And so this sets off a chain reaction, which results in downflowing air here. Which is then connected to the convection loop here at the top, because the high tends to have its air move toward the low. And then that low turns into a high as it compresses this air and smashes it down and creates a high pressure region here. And the high is attracted toward the low. The low pressure air rises up, experiences resistance at the tropopause, and becomes higher pressure air. And then that higher pressure air moves from high to low, and this process continues. So we get an onshore flow. This process can continue for several days until finally, but tends to happen after a few days of, this is typically in the summer this will happen, the fog will move up over the coast ranges and engulf Atascadero. And so once Atascadero then is covered with fog, that blocks out the light which is coming from the sun. This cools off, and that shuts down the convection loop. But this is something that often happens during the daytime. Okay, so we get an onshore flow during the daytime. What about at night? Well, at night, and this is something that surfers can tell you about, surfers like what's called an offshore flow, because that improves the shape of the waves. So the waves are coming in like this. And so if the wind's blowing this way, it tends to smash them flat. But if the wind is coming this way, it tends to give the waves better shape. And so that's what the surfers are looking for, is the offshore flow. And so typically what you have to do then is you wait until the evening, and then in the evening, the land cools off faster than the water does. Not only does it heat up faster because of a lower specific heat, it also cools off faster. So at night, this is cooler. And so relatively speaking, this is warmer than Atascadero at night. Not warmer than during the day, but warmer than Atascadero. Because a larger specific heat means it loses less heat, whereas this, I should say, loses less temperature, whereas here we lose a greater amount of temperature. There's larger temperature fluctuations, in other words, with lower specific heat. So that means that here we tend to get the evaporation, and the instability happens over the water. So this means that the air turns it from a downdraft to an updraft. Because this is now relatively warmer than in Atascadero. So this will tend to rise, expand, and cool. Okay? And so it goes from low pressure here to high pressure there as it expands. But then here at night, what's happening is that this region is colder, and so the air can move in from above, and so the air goes from an updraft to a downdraft. So essentially everything that was happening during our convection cycle during the day is reversed at night. But then this air, which becomes high pressure at the surface, because now this air is being pushed down on by the circulating air that came from the updraft off of the ocean, then causes at the surface this to be higher pressure than the lower pressure, which is down here in Morro Bay. And so this creates an offshore breeze. And so this will tend, somewhere in the evening, this will tend to shift from an onshore breeze to an offshore breeze. And then when it starts to heat up again in the morning, it'll shift back to an onshore flow. So the surfers then, as dedicated as they are to getting good waves, are willing to wake up at 4 or 5 in the morning and get out there when we still have the offshore flow, so that the shape of the waves is better. And they are able to get those good waves when there's just a little bit of daylight, because the sun has just come out, but before the sun has significantly heated things up in order to cause this offshore flow to shift back to an onshore flow. And at that point, the waves are not acceptable anymore for the surfers. And so they've lost their chance if they haven't gotten up early. And so this is the way in which these convection loops can shift locally if we don't have a larger global kind of a wind pattern that is interrupting it.